Do you want to learn about crystallography? Here's the history from the beginning. Our story begins in Munich in November 1895 at William Röntgen's house, where him and his wife lived. Here is how the story goes. While at his lab at the University of Würzburg, there was a cathode ray tube. Röntgen had the brilliant idea of having his wife put her hand under the tube. Then, 3, 2, 1. Röntgen knew he had made a great discovery. He thought he was a genius. This was the first X-ray image created by Röntgen of his wife's hand, which you can prominently see the ring on her finger. In 1901, Röntgen won the first Nobel Prize in Physics. At the speech, he said, "When this strange energy form is sufficiently investigated and its wide field thoroughly explored." Next, we will move to the events that occurred in 1912. Sommerfeld held a meeting at Hofgarten Cafe discussing experimental physics occurring, including the diffraction of X-rays by crystals. In the meeting, these physics scientists reached a consensus that X-rays should behave like a wave but not particles. In addition, they believe that crystals are made up from atoms arranged in regularly ordered, repeating geometric units in 3 dimensions. If diffraction and interference occurs when the wavelength of a light is a similar size to the width of the slit of an optical grating, and if X-rays were indeed waves that have a wavelength at least 10,000 times shorter than visible light, then in theory, the spaces between the atoms in a crystal might be just the right size to diffract X-rays. If all of this were true, von Lau thought a beam of X-rays passing through a crystal will be diffracted, forming a characteristic interference pattern of bright spots on a photographic plate. So, if 1. Diffraction occurred when wavelength is similar size to the width of optical grating, and 2. X-ray acted like a wave, then the space between atoms in a crystal might be the right size to diffract X-rays. Here's a figure demonstrating the whole crystal being imaged with X-rays to obtain a diffraction pattern. Here's an image of the first diffraction pattern gathered. However, there were a large number of points where these spots appeared to be missing. He suggested that the X-rays must contain only certain wavelengths to account for the missing diffracted beams. The news reached the Braggs in 1912 at their holiday site on the Yorkshire coast. William Henry Bragg, the father, then 50 years old, was professor of physics at the University of Leeds and had recently come back from Australia, where he'd been professor of physics for 23 years. William Lawrence Bragg, the son, was just 22 years old and a student at Trinity College, Cambridge. Lau's experiments puzzled them a great deal. William L. Bragg calculated the positions of the diffraction spots on the Lau diagram, using the well-known equation now called Bragg's law, and showed that the zinc blende has in fact a face-centered cubic lattice, and not a simple cubic lattice as had been assumed by Lau. It was this feat that opened up the possibility of determining crystal structures. Bragg's results were presented at the Cambridge Philosophical Society by the director of the Cavendish Laboratory, Professor J. Thomson, on November 11, 1912. They were a remarkable accomplishment for a 22-year-old man, still a mere student. The successful interpretation of Lau's diagram was not the end of the story for William L. Bragg. He started making experiments of his own, and during the spring of 1913 recorded in Cambridge Lau diagrams of crystals in alkali halides, zincblende, and fluorite, while his father, in Leeds, designed the first X-ray spectrometer using an ionization chamber. With the first X-ray spectrometer designed, by April 1913, the Braggs were able to record the first X-ray spectra. The spectra, which is made up of lines due to diffraction of the characteristic lines of the anti-cathode of the X-ray tube, which contains sodium chloride crystals. It is both from the Lau diagram taken in Cambridge and from the data recorded in Leeds with his father's spectrometer. W. L. Bragg determined the structure of sodium chloride. Together, father and son determined the structure of diamond as well, using both the Lau diagram and spectra recorded with the ionization chamber. They showed that the carbon atoms are located at the centers of the tetrahedra, the summits of which are also occupied by atoms of carbon. William Bragg also was able to solve two other organic compounds using the diamond structure that he saw. At the Royal Institution in 1924, J.D. Burnell was hard at work in his laboratory when he made an important discovery. He knew he had to pass it along to William Bragg. Of course, there's some math involved. W. L. Bragg continued his work in X-ray crystallography, but knew he could improve the technique. He just didn't know what it was until J. West, who was working in his laboratory, discovered something. In 1926, standardization of the use of the Weisenberg camera was completed by J.D. Burnell. The camera allowed for large amounts of diffraction measurements to be gathered, to be then used in 2D Fourier analysis. A few years later, in 1932, complex crystal structures of organic molecules were being determined, along with their bond angles and bond lengths. What's a story without some controversy? Everyone thinks Watson and Crick discovered the structure of DNA, but few knew Rosalind Franklin, who should have been credited with the discovery. Rosalind and her student were hard at work in John Randall's lab in 1951 when they made a unique discovery, later named Photo 51. Photo 51 showed a unique pattern which provided promising results in determining the structure of DNA. Maurice Wilkins, who worked with Franklin in the lab, did not get along well. Wilkins, without Franklin's permission, shared Photo 51 with Watson. The years following the distribution of the photo, Watson and Crick used it as the basis to determine the double helix structure of DNA. Watson and Crick published their structure in Nature in 1953, with a footnote acknowledging Franklin, but they took all the credit and won the Nobel Prize in 1962. hard to focus X-rays from a tube source. They are also only intense at particular wavelengths, which restricted their use in spectroscopy. However, a breakthrough showed up in 1947, when synchrotron radiation was seen for the first time at General Electric. It was first considered to be a waste of accelerator energy, but then recognized as X-ray sources that potentially overcome the shortcomings of ordinary X-rays. Nowadays, synchrotrons have become the go-to option for crystallographers. In 1971, the Protein Databank, or PDB, was established at Brookhaven National Laboratory and originally contained only 7 structures. It functions as a public database for macromolecular structures and has greatly benefited the scientific society ever since. In 2000, structures of both the small and large ribosomal subunit were finally revealed by X-ray crystallography. 9 years later, the Nobel Prize in Chemistry was awarded to the solvers of this complex puzzle. This is the end of the history of crystallography, for now.